Thank you very much for coming back from the lunch break. I hope you had a nice break. I want to talk today about the challenge of reconstructing digits in music score, and I want to dive right in there. So if this thing works. Ask me to? Yeah, that works. So the first obvious question from my side is why specifically digits? What is the interesting thing about digits and why I'm particularly talking about them? So digits play an essential role in music scores and they need to be reconstructed correctly, period. This is like a fact. And therefore, it's a necessary objective of any optical music recognition system. Regardless of what you build, if you do not handle digits, your optical music recognition system will be inherently incomplete. So I specifically worked with this problem at eNote, and I think it's an excellent example to demonstrate why optical music recognition is so complicated and so difficult. And already in this example, you can actually, if you look closely, you can see 3 classes of digits and 3 classes of text. So you can see the 3s that show a tuplet. The first 3, then you have the 3, 4, 3, 2, 1 on top here for fingering instructions, and then you also have the time signature at the beginning, the 3/4. So those are already 3 types of digits that you have to reconstruct in order to make sense of this small snippet of music. For the research that we've done and for trying to build our own optical music recognition system, we came up with 10 classes of digits that are of general interest. These are not complete or something, it's just something that we found most helpful in building an actual OMR system. So there are more classes than this, but for our works, we specifically were interested in basso continuo, those numbers that are below and indicate which chords to play, fingering instructions, measure numbers, multi-measure rests, octave transpositions, tempo numbers. I'm now in the second row. Tempo numbers, time signatures, couplets, volta numbers, and everything that is not one of these 9 classes went into the other class. And why these particular classes? Because if you want to reconstruct the musical semantics, these are the most essential parts you have to understand to make music semantics happen. For example, distinguishing between a tuplet and fingering instructions. So there are several challenges that I want to talk about, and the first one is obviously to find all digits in a score and to correctly recognize their value. This is primarily a computer vision problem, so we basically know how to do this, and we can solve this with modern deep learning-based approaches. So we have some really good results on these. But unfortunately, that's not the end of the story. What happens now is that we have to assign the digits to the right class. So this is already a computer vision and a musicological problem, because in order to understand this class of what this digit of these 10 classes that I showed you before, what it belongs to, you have to have knowledge about the musical rules and the visual and musicological context. So in this example, there is one very tricky thing. So I think the first example is quite clear. This 3 here is a measure number. Then we have fingering instructions, and in the end, tuplets. However, the second one in the middle, the second fingering, the 3, is actually a bit tricky, because if you just look at this from a visual perspective and don't have any musical context, it could also look like a 3 that indicates a tuplet. And you have to actually understand the musical context to make sure and understand whether it's fingering or tuplet. And well, if you look at these examples, you say, well, but it's like vertical and the triplets are usually italicized. Well, that's one of the problems that you've encountered when you actually try to do this on a bigger scale, that these rules that you think are in the scores are actually not there. So some of the other challenges that you will encounter is that some digits are simply missing. So with triplets, you have this rule of good continuation, and musicians are expected to know this. So you have like groups of triplets. So after the first measure, you just stop writing them, and the machine must understand that there is kind of implicit knowledge, implicit digits there. And finally, ambiguities. So there are multiple plausible explanations sometimes, and this is primarily a musicological problem. So the machine must actually understand the rules of music notation, that govern music notation, to resort to the most plausible explanation. And this is another example here where you can see fingering instructions and tuplets being like potentially confused by the computer. So on the left side, you have this 3, which is again at this very unfortunate position of the middle of the beam of a group of 3 notes. And unless you actually compute the durations of these, you could think it could also be a tuplet. And the example on the right-hand side, this actually is a triplet. But given the understanding that this is a singing voice, like a sung voice, it wouldn't make sense to have fingering instructions there. So there is more knowledge that you can put into place if you have that, but you can see that you already have to have a good understanding of the music to deal with this. So what we tried was, I would say, a bit naive. Still, it was worth a try to build a digit classifier with deep learning. And what we did was formulate this problem as an image classification problem. So we extract regions of interest where the digit is in the center. So we have 3 examples here at the bottom. And then we ran a state-of-the-art image classification neural network. We also try to fuse in additional information to help this problem, like the depicted digit, because we already know that. We already know there's 3 or 9, and some classes are incompatible. For example, you don't have a fingering instruction 9, because you typically only have the fingers 0 to 5, etc. So you can add more a priori information about this, and we trained it on a kind of large data set of 10,000 synthetic samples and 7,000 manually labeled samples that all looked kind of like this. And the results were really looking amazing when we trained it. And then we actually put it into production. It was like very disappointing. So we have around 60% accuracy, sometimes even less, which is definitely not enough in order to help us solve this in our semantic reconstruction. And some of the reasons why I think this was the case was because we didn't have an attention mechanism there. So we just fed the entire image. And the computer was just tasked on defining the class here. And we didn't say, look specifically at the thing in the middle, but just look at everything, because we thought the computer might figure it out on its own. But either the data set is too small, or we did something wrong with this here. We also experienced this once we started adding the manually annotated things. It got much better. And the whole contextual musical information that I just showed you an example before, with this like singing voice, etc., is missing. So these ambiguities and the missing semantic information force the network to kind of approximate for the most likely case. And when you look at the attention maps here, you can see that one of the things that I think the network learned was kind of to look at this kind of region that is in the right bottom corner for understanding measure numbers, because that was the most prevalent class in our data set. So it's basically a measure number classifier, if you will. So it kind of looks for these accidentals, and if it finds them, it, I think, guesses that it's a measure number. So that's not enough. So summarizing, classifying digit is a crucial step, but I believe that a purely image-based approach is insufficient because it's highly context sensitive, and we definitely need more information there to do this. So this naive approach is a starting point, but I think it's not enough. So machine learning approaches might be used for this, But if you want to try this, I would recommend that you make sure your network learns the right thing by providing more contextual information. Thank you very much.
Thank you. You're right on time. Does anyone have any question for Alex? I don't see any raised hands.
Yes, I have a question.
Yeah, go on, please.
Thanks for the presentation. Sorry, I didn't know how to do the raise hand emoji. I actually have two questions, if that's not overstepping. I'm wondering why you wouldn't use a smaller crop for the image, because as you said, having the entire score sort of gives it too much information. Did you try smaller crops?
Yes, so the small images that you've seen were, I think, like 200 pixels by 200 pixels with the digit in the center. And it was empirically, we haven't tried other crop sizes, but we thought, like, when we as humans looked at it, we got enough contextual information. So my reasoning was that if I do it in this size, it's kind of the balance between having small images that are easy to process and fast to train on versus giving just enough contextual information for the machine to do the right thing.
Okay, sorry, I misunderstood. I thought you said that you put the entire score in there. Okay, that makes sense. I do have a second, but I'll let anybody else ask a question.
Yeah, if nobody else, then you can go on. Jorge, has a question?
Yes, but Adrian, please go ahead and I'll have mine afterwards. No problem.
Yeah.
Okay, yeah, since you mentioned at the end that with the attenuation that it was always learning to look at the bottom right, I was wondering, would it make sense to just train a bunch of binary classifiers, one for every class, like yes or no, it's a measure number, and then I have a completely separate model, yes or no, it's a tuplet number.
Mm-hmm. You can do that. You will just multiply the effort of training by 10. And usually, given that these classes are exclusive, like either this or this, it kind of makes sense to just have one image classifier with 10 different outputs to kind of say that. I mean, we haven't tried it. I think it might be interesting to take a look at it, but I think it wouldn't be much more helpful, because the reasons I think that it's not working is not that you have like 10 classes, but that the network was not having enough information to do the right thing, or was looking at the wrong thing.
Got it. Thank you very much.
I have a question.
Yeah, who's talking?
Anthony Wilkes speaking.
All right.
Can you see me? I'm here.
Yes, please go ahead.
Yeah, well, it's not a question, it's a comment really. Thank you, Alex. It was a great presentation. I think you're absolutely spot on this digit thing. I'm from Organum. We do I'm talking later about it. It's purely a comment, but I've concluded myself that the digits are very little help in identifying plets of any sort, and that really there has to be an independent mechanism by which plets are found. Of course, the problem is even more horrific than you rightly describe, in that it isn't just a matter of the first bar having triplets and subsequent bars not. I mean, there might not be any marks.
Mm-hmm.
You know, I mean, triplets crop up perhaps with the first of the triplet is a rest on one stave, and the other two are notes on another stave, and there's nothing to say. You just know by, you know, light of nature. Anyway, it's just a comment. And thank you.
Yeah. So I think there is also like this idea you can basically ignore all digits whatsoever and just try to make sense of the music without digits, and then just use that information for printing. I think that's also a viable approach. But maybe you could tell us more about it, how you are doing in place. I'm looking forward to that keynote very much.